Thanks a lot to the organizers here to bring me here, and so that I can show you my or our status of the experiment, what we aim to go towards a Bell experiment. Whether it will be loophole free or not, that will be judged later. Let's put it that way, but let's see what we are doing. I mean, yesterday we heard already by Jean that how theoretician's view of a Bell experiment. He said also that don't think about the experiment, think about the data, which is of course one approach. I just want to show you how to get to the data. What I want to mention first, of course, is the work of my students and collaborators. So most of the experiment, what I want to show you today is the results, experimental results, was done by Julian Hoffmann and Michael Krug. And in a moment, Norbert Ortegel and Kai Redeker, they are the PhD students now here, and they are working on it. And actually Daniel Burchardt, I completely forgot. There's still one more PhD student now, of course. Lea was with us for master students, and the group is led by Benjamin Rosenfeld and Markus Weber, and it started before with Christian Kurziefer and Jürgen Volz. So what I want to show you is first the concept basically and how we get there at all. So all of course started now with the idea that quantum mechanics is not complete, and that Bell showed that there is a way to distinguish between this, what he called theories with local causality and quantum mechanics or all the other, whether those theories are correct. And the first tests now are done almost pretty soon afterwards. Now, all these tests, and many, many, many more tests, of course. And all these tests, of course, suffered by those famous loophole or unfamous loopholes that the detection probability of the two components was way below unity. So that means that there's always the option that you can make up a hidden variable model which simply takes the detection or no detection into account, and then it's very easy to show that you can fake the results, the seemingly quantum mechanical results, also with this local hidden variable theory. So you need detectors with a very high efficiency. And then, of course, there is the independence between the two observers now, if I may to use this word here as well. So if we have the two observers, the two measurements, I mean, they really should be independent of each other in the term what's also defined by Bell. Now, actually, these loopholes have been closed, but only one in each experiment, in different experiments. So the first, which had very high efficiency on the detectors, was measurement of two entangled ions. First, even so close together that you could not resolve them optically, so you just got a signal where you knew that it is from two ions. That was done in Dave Wineland's group in 2000, and later then in the blood group in Innsbruck, really with two separated ions, so that at least you could resolve them optically. But still, I mean, the distance between these two ions was about 3 micrometers, so it's way below anything what you could assume to be independent at all. Now, independent observers, we tried to do in Innsbruck some time ago, where we distributed two photons along the campus of the Innsbruck University here. The distance was then about 400 meters, and the observers, they consisted now of some random number generator, and which controlled a Pockl cell, which determined then the analysis direction. And so fast that the time it really takes from tossing the coin, more or less, to finishing the measurement, really with the detection of a microscopic signal. So many electrons which come out from your APD, then from these photon detectors. So this time span is on the order of about 100 nanoseconds, and so that's much, much shorter than more than a microsecond distance between the two observers. So there surely could not have been influence which propagates at the speed of light here. But in this experiment, of course, then the detection efficiency was only 5%, and this is way too low to close this loophole as well. So can we close both loopholes? Actually, there are experiments now going on with photons. So more or less similar what we did in Innsbruck, now perhaps on a shorter scale, but the detectors are very fast. So I mean, this 100 nanoseconds, I mean, allow you to make the experiments on a distance of, say, 50 meters only as well. So there are two groups, actually, Paul Kwiat and in the Vienna group of Anton Zeilinger. Now they try with new detectors. These are superconducting detectors which change from superconducting state to a normal conducting state just due to the absorption of a single photon. It's still a miracle to me. But anyway, they do it. And so with these, you really can detect the single photons with a very, very high efficiency. So it's more or less close to unity as well. And these groups are now trying to make these experiments with these systems. We are following another route. So we more or less start with the idea of detecting atoms. So why can we detect atoms so easily, or what was done in these ion trap experiments? If you shine light on an ion, then depending on in which state it is, it will scatter off light or it doesn't. So either it's bright or it's dark. So in a sense, it's like perhaps even kind of amplification of the state, like what Nicola had in mind, that you really, depending on the state of the ion, you either see many photons or you don't see any. So this was done there, and we thought, okay, let's do it this way. But there are two big buts what we had to overcome now. We have to distribute it, of course, this entanglement. I mean, we have to change effectively completely the scheme of the preparation from these old experiments in a single ion trap. And the fluorescence detection is relatively slow. So I mean, you have to scatter off a lot of photons from this ion, and you have to collect all of them. And until you collected enough photons so that you really can say yes or no with a high precision, it takes a while. And so this, in our experiments on the moment, is 20 milliseconds. So admittedly, there are ion trap experiments which achieve this within, say, 1 millisecond. But still, it's relatively slow, given that your detection now, your measurement now takes a millisecond. And a millisecond would mean quite a significant distance between the two observers. Okay, so that's now the developments. What I want to show to you now is what we are doing now to get this detection below the microsecond, not even millisecond, but really below the microsecond level. And if we have a detection below the microsecond at the microsecond level, then we can go for a distance corresponding to a microsecond that's then 300 meters. Okay, so that's the goal. And what I want to present you now effectively is still the status, as I said, the status of experiments which go towards this goal. Okay, so first, distributing entanglement. For our way to distribute entanglement, we really want to get atoms entangled now at the distance of this 300 meters. And of course, I mean, usually we can entangle atoms letting them interact, but then we cannot bring them apart anymore. That's not possible at all. So we need something different. The way what we are doing is we want to teleport the entanglement, or rather use this, what's called in quantum information, entanglement swapping. So teleportation works like this, that if we have a quantum state on this incoming particle, then we can transfer the state to this particle, which is here called number 4, simply by doing a Bell state measurement, so projecting them onto this incoming particle with another one, this particle number 3, onto an entangled state. So this projection onto an entangled state gives me some result from which I can infer the state here, which is up to some unitary transformation equal, local unitary transformation equal to this incoming state. So if we have this option now, then we can continue this. Actually, because if I have now 2 pairs of entangled particles, and if the particle 2 is entangled first with particle 1, and if I can transfer the state of 2 to 4, then at the end 1 is entangled with 4. Okay? So, and that's the idea of entanglement swapping. So we can entangle 1 and 4 together, if we have entanglement before between 1 and 2 and 3 and 4. And the main experiment what I want to show you now is really that we are able to do this for the atoms now. But evidently, we can now use the 1 particle and the 4 particle as the atom. But if we want to do this for a big separation, then we have to bring particle 2 and 3 together, which simply means there we really need photons, because we can transfer only photons over reasonable distances. And so therefore, we first have to start with entanglement between an atom and a photon, and evidently another atom and another photon, to really achieve this feat here. Okay, so how do we get the atom-photon entanglement? Again, interaction. In quantum information, we're used to quantum gates, but we don't have this a reasonable thing for atoms and photons. So what we are using actually is something like a decay. If we have a transition between an initial state and 2 final states, so from an initial state and 2 final states, then obviously we have 2 options for emission of the light and then the final state of the atom. And that's what we are using. So we have a kind of scheme where we have an excited state and then 2 final states, and the emission of the photon, then the state of the photon will be entangled with the final state of the atom. And the way we are using it is that we are using the polarization of the photon, because we can handle this relatively easy, and it's pretty stable even over long distances, and the internal state of the atom, so it's kind of spin state, the magnetic sublevels. So now the actual scheme what we are using, the real atom now is a rubidium 87, and in this rubidium 87 there are many levels, but the ground state here has this f equals 1 level, and it means here we have 2 magnetic sublevels with spin -1 and +1. And if we have a photon emission from this excited state here, 0, 0, down, then we have either this right circular polarization and a magnetic sublevel -1, or the left circular polarization and magnetic sublevel +1. And we don't have to worry about emission up to additional noise, but never mind. We don't have to worry about this additional emission here, because this is, according to the dipolar shape of the emission, goes into an orthogonal mode. And if we sample light only in a horizontal direction here in this plane, then we really sample only the circular polarization and not this linear polarization. So we really get at the end this here. So the experiment looks somewhat like this. Here we need a single atom. Actually, to get a single atom by now is almost as easy as getting, or is it actually it's much easier than to get BECs. It's because you start off with a very lousy cloud of atoms. Does not need to be this high quality what you need for BEC, just a magneto-optical trap, and then you shine in light with a red detuned laser. That's very fashionable now in biology. It's called these optical tweezers, what they use to manipulate anything below their microscope. And with this optical tweezer, we shine into this cloud of atoms. The tweezer, in our case, is well focused. So it has a volume only of about 2 microns and 3 microns, cigar shaped. So that means that the atom now is caught in this regime, because there's still this kind of friction of the magneto-optical trap. So with this scheme, we can really get this atom with our optical tweezer here, and it's hold there. And with the same optics what we use for this trap light, we collect the light. So this more or less makes sure that we get a well-aligned system and mildly efficient collection efficiency. And then we need additional laser beams. So one to prepare the initial state. This excitation evidently is the one which brings us up to the state from where we can then observe our emission. So this fluorescence then is collected in the single mode fiber, and then we can do polarization state analysis of the photon. So whether it's left or right circular polarized, or in any superposition of it. But this we of course have to do also for the atom. And this now is a little more involved, but it's relatively simple still, because if from this state initial state, we go to the -1 with the right circular polarization, then that means that if the atom is in the -1 state, then we can excite it only with right circular polarization. If we shine on the +1 state, right circular polarization, there is no level up there where it can be excited to, so that means that it's dark. So there will be always, if we shine light on with a certain polarization, there will be always a bright and a dark state. And effectively, the polarization of the light, what we shine in, determines what type of superposition state for the atom we can really detect. So for example, if we shine in right polarization, we detect the plus state. If we shine in left circular polarization, we detect the -1 state and the +1 state. And if we shine in any superposition, so that means linear polarization, then we can talk also to any superposition of these two states. So with this, we can really make full state analysis of this atom without any need for this local unitary gates. So this is the whole sequence of light pulses, what one has to do. So in here is this emission of the entangled photon, of the photon entangled with the atomic state. And then this is this polarization-dependent state analysis, what I mentioned before. And from there, actually, in the experiments, what I show to you is actually with this polarization-dependent light, which only make a transfer from the first ground state to the second ground state level. And if the atom is in this f = 2 level, then we can push it out. Okay, so we heat it, we shine light into the trap, which only talks to this f = 2 state, and which pushes the atom really out of the trap. And then we shine on, we turn on the magneto-optical trap light, and then the atom will scatter if it's still in, or it doesn't scatter if the light if it's not in anymore. And this is our detection signal. And so all this together takes still quite a while, but never mind. I mean, the detector is very efficient. So anytime where we are asked to, we give an answer, yes, the atom is in, which we say, okay, that's this state, or no, the atom isn't in, which is the orthogonal state. So effectively in this scheme, in this sense, we have a detector with 100% efficiency, or let's say for a Bell experiment, we give an answer every time where a measurement is done. So in this now can be done here, that we show the entanglement of this state with this making state tomography between the atom and the photon, and we get a fidelity of 87%. So this 87% is not arbitrarily high, of course, it's not 1, but it's good enough for any Bell experiment. Then, and we know that the main contribution for this lower value, somewhat low value, is due to this not so perfect state transfer. So effectively, all the other steps have relatively low noise. It's still just the state transfer, the state-dependent excitation, what I mentioned before, which is not so perfected. Okay, so this is how it looks in the experiment. All and everything happens in this glass cell. So this is just a glass cell of about 3 centimeters by 4 centimeters. And so here's this microscope objective what we use to focus the light for our trap beam into, and where we sample the emitted photons with. And all the many other light beams now are just for this excitation analysis, etc., etc. So what can we do next? Now that was just one atom and one photon. Now you have to convince all the funding agencies that you need all these toys another time. And so to get another atom and another photon, and that's now actually still in the same building, but in another room. Actually it was built up again, took another almost the same time, unfortunately. And the two positions of these glass cells now in these two labs are about 20 meters apart from each other. Okay, so and the goal now was to get entanglement between these two atoms in these two cells, which are trapped and manipulated by effectively completely independent setups. So each of the two setups can run its own program and actually does run its own program. They only are synchronized via some synchronization signal, which comes, in this case, no, they have a common, sorry, the synchronization signal comes every milliseconds, and then they have a common clock with 100 megahertz. So but that's the only connection between these two experiments. Everything else is done completely autark on each lab. And then, of course, there's the connection with the optical fiber. So the photons which are created in this second lab here from Atom-2, which is called in the, they are brought over here into this first lab. So this Bell state measurement then is done here in lab 1. So and this is how it works now. This Bell state measurement for photons can be done relatively simple. That was done, or all the photon experiments on teleportation, etc., use this scheme to make interference at the beam splitter. Now, this interference at the beam splitter, this allows you to see, to detect 2 of the 4 Bell states, but this is enough. The other 2 cannot be detected with this scheme. So, and this here roughly gives you also the scheme here. The experiments are controlled locally and with this common clock of this 100 megahertz. And then there is this excitation pulse, and then the atoms are excited. And we repeat this very often. The collection efficiency for a photon from one atom is only 1/1000. Okay, so only to see that, to get really this entangled pair between an atom and a photon, that has an efficiency only of 1/1000. And if we have 2 traps, then evidently we have to repeat our excitation, this pairwise excitation, 1,000,000 of time until we really get 2 atoms detected in the middle. But eventually, I mean, we repeat this, this here on a 50 kilohertz time scale. So, and then it takes a few seconds until we get this 2 photon detection here in the center. And that's good enough. What you see here on the right is one of the steps what you now have to take if you really want to have good interference, because if you want to have interference between these 2 photons coming in, of course, there shouldn't be any way to distinguish which of the 2 photons came from which of the 2 atoms. Otherwise, you wouldn't get interference. So, and one crucial thing is that the time dependence of these 2 atoms is next to indistinguishable. So this picture was taken that depending on some trigger from relative to this clock here, this atom was excited and then detected. That gives the red curve, and then the other atom was excited and detected. That gives the blue curve. So that's the time shape of these 2 photons is really identical, and the other requirements then is that also, of course, the frequency of the 2 photons should be indistinguishable up to some scale, and then also the spatial mode overlap is taken into account easily with this fiber beam splitter here. So these are the requirements now that we really can expect good interference. So the next step is that we still have to check whether our atom-photon entanglement really still is good enough. So for these measurements here, is always also individually measured. So first, we excite the atom in trap 1 and measure the entanglement of the atom relative to the photon what emitted is. So that means for this measurement, for example, here, these 2 detectors, they have been aligned at H and V polarization, and the other one at plus and minus 45 degree. And then you get 4 curves for if you analyze now the atomic state, either at say some relative angle 0, then you see perfect correlation or anti-correlation with the H and V polarized photon. And if you rotate this analysis angle by some 45 degree, then you see perfect correlation or anti-correlation with a plus minus 45 degree photon detector. So that shows that our atoms and photons are well entangled, and here with actually with a relatively high visibility now. So this was improved now from this initial value. Now we are slightly above 90% even. So and now we really can look for this case that we look at this two-photon detection here. That means the projection of onto an entangled state for the two photons, and then the two atoms should be entangled. And then really what you see now here, if we analyze the atom in trap A, so that's now angle alpha, say at 90 degree, then we see perfect anticorrelation here if we analyze the atom B also at 90 degrees, and vice versa. And this is for the two different Bell states what we can analyze at this two-photon interference. The visibility of this experiment now altogether was this 81%, and this allows you, with this data shown here, gives you a violation of the Bell inequality from 2.19 relative to 2. It's a Clauser-Horn-Shimoni-Holt inequality, and the error here is reasonably low, let's put it that way. Okay, so what does this experiment show you now? We have now two atoms entangled with the observation of these two atoms with perfect detection efficiency. Really, we give an answer always when there is a trigger in this two-photon detection. So with perfect detection efficiency over 20 meters, now we can show this violation of the Bell inequality. So that's 20 meters and perfect detector. So what I said is before is we now need, of course, a larger distance and much, much faster detectors, because the detection procedure here takes about this 20 milliseconds. So how to get there? So I first show you the detection system and how to get there way below this value. So we don't rely anymore for this new detection system on the fluorescence detection, because that's way too slow. So what we are doing now is we simply ionize the atom, and then we collect the fragment, so that means the ion or the electron. And you see this is really now a picture of the new glass cell, which is not yet in the experiment, not this week, perhaps next 2 weeks, honestly. But this was tested now in an external lab. So where we have here this called channeltron, so it's kind of electron multiplication unit. So that means this single electron which comes in now gives you then an output pulse of about 10 to the 5 electrons here at the output. And similarly, the ion which is collected here gives you another 10 to the 5 electrons. And if you detect either this signal or that signal, this now gives us then whether we could ionize the ion. That means that it was in this state, or we couldn't. So the scheme is now like this for these test measurements, that we first try to ionize it from this f equals 2 or from the f equals 1 state. So remember, we still need first the transfer, this polarization-dependent transfer here, and then from these two states we make this separation here. And this can be done with fascinatingly high discriminability. So if the atom is in state f equals 1, then we have hardly no excitation. It's below 1% ionization probability. It's really below 1%. It was on the order of 6 per mil only. And we get about higher than 99% ionization probability within about 300 nanoseconds. So we now have a better laser system, so we are down at about 250 nanoseconds now. And the other thing now is we have ionized it with this laser pulse. Now we have to collect the ion and the electron, and to do this, then we have to wait quite a while, actually. The electron, of course, it's accelerated immediately into this channeltron detector, and then gives you this output pulse, which takes another 100 nanoseconds, but never mind. But it takes a while, actually, to get the heavy ion moving and into this channeltron. But still, altogether, so this including the time of flight and then also this amplification procedure here, it takes about 400 nanoseconds to get the signal once the ionization took place. So that means now we have a very high detection probability and discriminability. So altogether, this analysis probability for our ion, where we have been actually quite lucky, because I mean, it's not your business, but afterwards, many people told us that this ionization detection never can be made so efficiently. But we profited from the fact that we don't look at big clouds, but rather just really at the tiny spot, this 2-micron spot, and this then effectively turned out that this can be detected more easily. But never mind. That's experimental details which sometimes are positive. Usually not, but sometimes they are. So what we achieved now is we have atom-photon entanglement, and also we can stabilize a 300-meter fiber for polarization. That's possible. We could synchronize these setups, and we could demonstrate the entanglement swapping. So we really can make in 2 independent setups the 2 entangled atoms. And now in a different setup still, we also can show that we can make this fast detection. So actually, what we are working now since the last half year, or a year almost already, since this data, the initial data have been collected, now is to rebuild everything so that we can get another fast detection for these 2 setups. And also we had to get a new lab then, of course, because eventually, if we want to make this experiment loophole-free, we have to implement this ionization detection, and we also have to make fast measurements. So this is still the weak point in all our developments, or the latest point. So we need a new random number generator, more or less. We have the scheme, but we want to improve on the readout concept. And then we have to go for the long distance. Because if we now can detect our ions within, say, this 1 microsecond, well, a little below 1 microsecond, but say we can detect it within a microsecond, it requires the 2 observers to be separated by 300 meters. So where do we get the 300 meters? Actually, this is the area of the university in Munich, the main buildings of the university. Detlef's office slightly out of the picture already, some other 500 meters away. But unfortunately, we are doing quantum cryptography experiments to these buildings, but we couldn't, there are no fiber channels going there. So we could not use these buildings there for our purpose, so we had to find another place. And actually, it's up there. It's economy department, but there have been some miracles that we got a lab at the economy department building. And the other good thing was that, contrary to Theresienstraße, there is a fiber channel actually now. Really, there are cable channels from old phone lines and so on, etc., between the 2 buildings now. And actually, it was just a week ago now, really, it's not that I'm cheating. A week, and these 2 buildings now, they are 396 meters apart, and a week ago now, finally, we could bring the cable into this new lab, which was renovated for half a year or so. But now we really have a fiber from this lab to the other lab, and now we can start moving our experiments there. Don't wait for the results tomorrow. So my optimistic estimate is a year about. If you talk to Benjamin and Markus, they will give you a slightly longer number, but never mind. We are on the way. Thank you.
Thanks, that was a great talk. So you started by saying something about the sort of theorists and philosophers versus the experimentalists, and I want to try to connect those up a little bit, because I think there's an issue that sort of often comes up in the discussion on the theory and philosophy side that actually you're in a much better position to say something useful about. And what I mean is the assumption that everybody knows that goes into deriving a Bell inequality that's sometimes called the no conspiracies assumption, or the free will assumption. And I think the usual way of looking at it is that that's just something the theorists and philosophers have to assume in order to derive a Bell inequality, and then the experimentalists go and tell us whether Bell's inequality is violated, and there's the loophole about locality, and there's the loophole about detector efficiency, and so we sort of want to make sure those loopholes are closed. But to me, it's, if I already knew which fundamental theory was true, then maybe I could go and look at your experiment. And by the way, also not only if I knew which theory was true, but if I sort of could see exactly what the state of every microscopic degree of freedom in the world was, then I could go see whether indeed this other assumption that goes into deriving Bell's inequality is true in your experiment. But of course I can't do that, and nobody can do that. And so it seems to me that the experimentalists are the people who are in a position to make some kind of case that the free will assumption is reasonable, and in particular to make a case that it's reasonable regardless of which sort of fundamental candidate theory one might contemplate. So can you say anything about that?
Yes, I mean, I see some reason behind the free will concept, yes. On the other hand, I have to say that our experiment, at least not in this stage, what I even hope to get done by the year or two or something like this, will be able to close this free will issue. It's what I show you here now is roughly what we have here now is the photons are collected from atom 1 and 2, and then we have to communicate still this classical information about the result. Now, we just continued this line here, but these lines are electrically or optically signals, and they are surely slower than the speed of light. Okay, so the speed of light is not shown here, but it is slower than these lines. It's more flat than these lines here, which means that from this point here, there is already information at the measurement positions that there will be the projection, that the projection happened before we come there. And so therefore the random number is created only after this.
Yeah, so in other words, the so-called free choice is set by some quantum random number generator or something like that.
Yeah, so it's not like what Harald Weissman showed us today, that the random numbers are created outside the light cone of the source.
Right, but
wherever you define our source now, but at least at the projection of the two photons.
So the worry though is, or at least the thought is that there are many people in this room, for example, who would contemplate quite seriously the possibility that even a so-called quantum random number generator is actually fundamentally a deterministic process where there's something else going on in the past that determines, whether you end up measuring this or that on a given case.
Yes.
And I think, one wouldn't want it to be the case that one was sort of assuming the completeness of quantum mechanics in justifying the applicability of the no conspiracies assumption to the experiment. Does that make sense?
Yes, actually that's also why I'm happy to talk here, actually, because we are very open to any ideas to improve our experiment or to make it better, let's put it that way. So don't worry, and please come and I'll give you any information what you need. I'm very open about this. We just want to have maximum input from your side as well, what you would like to have done in an experiment like this. But as a matter of fact, in a moment, we cannot close this with a reasonable concept. There are ideas which make many more elements of the experiment way more complicated, particularly distribution of the optical signals, because all this has to be done then not through cables anymore, but really with free space optical signals. And this is way more complicated and not so easy in this layout. So I'm not quite sure on which time scale. I mean, we have plans, but I'm not quite sure on which time scale I can promise you to close this free will issue.
Frankly, I don't think you'll ever be able to.
No, it depends on where you set your start point. Yes, but I mean, eventually. I mean, there are always ideas out that we use some quasars or whatever as light source for our random number generators, but still, yeah, we can go on for this as well. Even in Munich, sometimes you see light and stars. And
What about experiments with the entangled states involving three particles, as proposed by Zellinger, where they say that with only one measurement you could see non-locality? What about this?
We made these experiments long time ago. I mean, see, a conclusive result, this one single measurement, I mean, of course, can be done only if you first prove the ingredients of these steps. So it's the last line is more or less just the consequence of three initial lines. And so only if you have proven these three initial lines, then a single measurement will give the contradiction. Now, we can even prove the first three lines, even in finite measurement time, never perfectly. So that means it will be always a statistical answer only. So even there, this single measurement, that's a fairy tale, actually. And it's not possible in a real experiment, definitely not. But even so, all these measurements on three entangled particles, they are way more complicated, and I don't see an issue to go for this. The complexity of the experiments is way beyond these experiments, and we are happy to handle those now. So.
One more? No, there was just maybe a clarification. So basically what you're saying is you're never going to close the free will.
No, the free will loophole is defined. The free will loophole issue is defined. This conspiracy, this eternal conspiracy all the way to the Big Bang or something like this.
Well, there might not be, we don't know, but nevertheless, I mean, what I was kind of hoping you might say is, nevertheless, it would be crazy. You'd have to be insane to think that, you know, that's the right way to understand what's going on here.
Oh, I did not dare to say this to you now.
And I mean, I don't think anybody in this room does think that, so it's not like that would be offensive.
This issue we can forward to the conference session. Yeah? Okay, good. So let us thank you.